Right.
Okay. I think we are live in all the places we need to be live, and that's wonderful. So I see a whole bunch of participants who've shown up. That's excellent. We've still got 1 minute on the clock, so I'm going to wait for people to find their seats, grab their coffee, or whatever is your preferred beverage.
This is just so much better than recording a talk, right? This is just so much more enjoyable, I think.
Oh, so much better. Yeah, no, I hate talking to my screen. I'm tired of.
And the absolute worst is when you can play it back again and then you catch all the glitches.
Oh, but, I mean, Leslie, for you, maybe just tired of recording. For us, like a cruel and unusual punishment. For people who are not native speakers, this is just a cruel and unusual punishment, recording a talk.
I absolutely understand that. I'm grateful that I can speak my absolute native language.
So welcome everyone. I'm going to start by just sharing my screen and start with just sort of the PowerPoint announcing that we are officially in the Test of Time panel, which will be followed by the awards ceremony. So thank you everyone for showing up. Thank you for our Test of Time award winners. Thank you for our panel who've made the time. Thank you for all the participants who are on the line here. So I think if you're here, you're here for a good reason. You're aware of the Test of Time award. You're aware that this is the second year that this has been given, because this was really an innovation that Mark introduced last year. And to me, it was actually one of my favorite parts of the program. It's one of the things I've gone back and watched a couple of times. And so I have aspirations that we can kind of live up to that. And certainly we have a spectacular paper, which was selected by the Test of Time Award panel. I should say, Test of Time Award awards committee, and this is the famous SARSOP paper, SARSOP Efficient Point-Based POMDP Planning by Approximating Optimally Reachable Belief States by Hannah, David, and Wisan, who are right here. And we've also got a panel, and you've probably saw the panel, and these are, of course, very well-known people in our community. But we have Leslie Pack-Elwing of MIT, Ron Altarovitz of UNC, and Danny Halpern of Tel Aviv University. So I am not going to take, you've had enough of me talking. So what I thought I would do is I would start by just going through each of the panelists and having them talk about a little bit about their perspective on planning. Some of them are already world experts in planning or planning under uncertainty. So let me start with Leslie. So Leslie, my understanding, at least from my sort of personal subjective view of POMDPs, is that you were the person who kind of made this connection, or at least that's my reading of the literature. Is you'd said, hey AI people, hey robotics people, you're trying to think about intelligent behavior. Really, here is an appropriate model to think about planning and thinking about getting your robots to behave well. Maybe I've mischaracterized that. Maybe I haven't. Tell me about your sort of perspective on the problem and your perspective on the work, please.
All right. Well, thank you, Dylan. And first, of course, I want to say congratulations. You know, I have to get in the right mode here. Okay, good. So, you know, I'll tell you guys, everyone in the world, a secret that the password to almost all of my group's computers in some way or another that is shared is POMDPs are hard. That's like our watchword, right? POMDPs are hard. That's how we think about things. But really, Hannah and David and Wisan have shown us that maybe they're not as hard as we think. And so first of all, I want to say something, which is that there are a lot of people who say, well, yeah, you know, you guys, you talk about POMDPs, but I'm not going to use them because they're too hard. And I want to actually just, first of all, advocate for a different viewpoint. So I want to say that basically almost every single problem in robotics is sequential, right? You have to make more than one decision. It's stochastic. We don't actually control the specific outcome that we get, and it's partially observable. And so really, I think if you work in robotics, whether you like it or not, what you have is a POMDP. Now, you could choose to ignore that fact or to not model it as such or something, but really this is the problem that you have. Okay, so I'm gonna now just use, this is an old trick for organizing talks in a certain way. And I have to say that my colleague Tomas and I were talking about what I was gonna maybe say today, and he gave me this powers of 10 idea. So let's talk about states and POMDPs. So one of the first papers really about POMDPs was due to Sondic and Smallwood. And Ed Sondic really gave us the framework. It's beautiful in the OR literature and the kind of nice algorithm. And they solved the problem with 3 states and 4 actions. Okay, so that's on the order of 10 to the 0 states. So much later, Michael Lippmann and Tony Cassandra, 2 of my students, and I, we went looking in the literature, and we got a tip off from someone in OR that there was this really interesting connection available in the POMDP work and the OR literature. And so Michael developed this new algorithm called the witness algorithm. And in that, our first paper, we solved, problems with 10 states. So that was pretty good. It was more efficient than Sondic's algorithm. Later, we tried to do some stuff involving a real robot, which I'll talk about just very briefly in a minute. And we wanted to solve problems with 100 states, but we couldn't use any exact algorithm at all. We had to just make up a bunch of hacks, one of which is QMDP that people end up using for various reasons. But we couldn't apply any really respectable POMDP algorithm at that time to problems with 100 states. Okay, so we fast forward to the 2008 SARSOP paper, and suddenly they're solving they're solving problems with many more states. And so that seems like really, it just made a huge difference. And then, there's Despot later, which lets us do kind of continuous states. And then they went on and handled continuous observations. And then Hannah more recently has been doing continuous actions, right? So I feel like, our ability to address problems has just grown enormously. So I just want to kind of show you a couple of simple POMDPs, and then I'm going to get out of here. But so in terms of robots, right? So I think the first time that somebody used POMDP for a robot maybe was us in '96. And so we had this trash can of a robot, and it needed to navigate around our building in Brown. And this was our model, right? So this was the building it had to navigate around in. And so it had, I don't know, 100-ish states. But again, we couldn't address that with any existing software at the time. So we just kind of made up some hacks. Later on, we tried to, and basically based on this experience, I had given up on POMDPs. I basically decided that these kinds of models were much too hard and I wasn't going to do it. And so then I ended up back at MIT and working with Tomas, and he said, well, maybe that POMDP idea is not so bad. So we tried to get formulate a problem using POMDPs. And so we kind of did this thing with Kai-Jen Shao, which was trying to figure out how to reliably manipulate something based on the contact sensing and so on. And we worked really, really, really as hard as we could to reduce the state space, to construct a reduced state space, because we figured that we wouldn't be able to solve problems with a large state space at all. But then almost immediately after this, the SARSOP paper appeared, and the SARSOP folks actually solved this problem very nicely, very efficiently, much better than what we were doing there. So there's been a huge robotics impact of this work. And I think one of the important, it's due to a constellation of reasons. One is that the algorithms are insightful and good. Another one is that they made great downloadable software that works and people could really use it. And so that has resulted in really a large number of robotics applications by a lot of researchers and practitioners. And I think the critical message, which came out very nicely in the plenary talk, is that although POMDPs are hard, they can really be addressed practically if we exploit the relevant structure in our problems. And so I just want to, nod again to Hannah and David and Wee Sun and say it's great work, and I'm really happy that they have done it.
Thank you. That's great. So I guess First, let me start by saying, Hannah, David, would you like to respond, or do you have some sort of comments? Or Leslie and I were talking a little offline, and I said it would be great if we could kind of get a little bit of a run up to some of the history before, as David said in the beginning of the keynote. If you read all the introductions to the papers, they say they're intractable, and so we've seen a little bit of what was around for that received wisdom. There had to be a myth made for you to bust the myth, right? And so I think this is do you guys have any reflections on that?
We'll let Hannah to go first.
Well, so I think at the time, I just finished my PhD at the time, and my PhD was on sampling, but for deterministic motion planning. And then I think David sent me the PBVI paper, which is sampling, but for POMDP, right? So I thought that's actually a very nice segue, because I was thinking that I think for building up my career, I want to move a little bit further from the deterministic planning. And so it turns out that there's a lot of insight that we can gain from the sampling in deterministic motion planning that we can carry on to sampling in the POMDP domain. And that, I think, helps a lot in getting it to be where it is today. That's from my view. I think the sampling helps a lot. Does that sort of?
I totally agree. If I may jump in over here. So let me first put in the context over here, right? So we learned POMDP from Leslie. And for me, definitely. I applied, after I learned POMDP, I applied it, the only algorithmic trick that I know of, sampling, to it. That's roughly what starts up, how starts up came about. Now, before we worked on POMDPs and planning on uncertainty, I worked on motion planning and the classic geometric motion planning. The challenge there is a high dimensional configuration space with for robots with many degrees of freedom. There we used the sampling again to overcome the challenge of a high dimensional space. Right. So when I recognize the one real difficulty about POMDP planning is this high dimensional belief, then it seems natural to think that sampling may be worth a try, right? And now this is a place where the beauty of mathematics, right? So the abstraction that says, well, this is if the core challenge is the high dimensional space, then an algorithmic technique that applies in this space may apply to the other space as well, even though that they differ in the physical details. So we tried, and really later on, after we worked on other tools, algorithmic tools, and to overcome the challenge of high dimensional spaces. But one thing nice is, well, the high dimensional space is really just hard, right? But in terms of developing algorithms, especially at an abstract level, really there are a limited number of general algorithmic ideas for that, right? So in a high dimensional space, we can sample, we can try to factorize into lower dimensional pieces, we can develop functional approximations that will be more recently neural network and other things, right? So these are the primary algorithmic tools one can deploy to overcome these challenges, and over time we pretty much try them all and have, like what Leslie just showed, the progress that brought us today.
You're muted, Wisan.
Yeah, I think you're
muted.
We don't hear you. No, we don't have any audio. We did get audio when you joined at first. It may be that your device is disconnected. So tell you what, let's give Wisan a little bit of time to figure out the technical gremlins, and I'm gonna segue to kind of have Danny give a bit of an introduction and a bit of his point of view. partly because I thought that, it would be good to have someone who, on the panel, who's sort of an expert in this, in what David had said, sort of this traditional motion planning, someone who really is an expert in thinking about the geometrical side. And one of the things that I kind of observed in looking at the keynote there is that geometry doesn't show up explicitly in the model in any place, really. There's discussion in the subsequent work about continuity, continuous actions, continuous observations. Of course, that action model and those observation models somehow have some of these geometrical aspects to them. What I hadn't kind of gotten was this thing that David just said about maybe a lot of the fresh ideas are developed and these few golden ideas are developed in the geometric space, and then some of them port effectively to POMDPs and some of them don't. Danny, what are your thoughts on sort of the relationship between someone who's a geometer with a big G compared to maybe a probabilist with a big P?
Okay, so indeed, when Dylan asked me to join the panel, I told him that I'm no expert on POMDPs for uncertainty in robotic tasks. So Dylan suggested that we discuss planning more generally, and of course I like it. I want to suggest a few topics for discussion and ask the winners. I, of course, congratulate them on this wonderful achievement, Hannah and David and Wissam. And perhaps before I put forth the topics, let me just say a few more words about my background. I started in industry. I worked on kinematics and trajectory planning for robot arm manipulators in the automotive industry. And this rolled me to do a PhD in the theory of motion planning. And you will laugh at it because I spent many years on planning an algorithm for the motion of a polygon translating and rotating among polygons in the plane. And I even didn't accomplish this in my PhD. Only a year after my PhD did we publish a paper with still the theoretically best results for this. But this got me into computational geometry and the study of arrangements of curves and surfaces. And then there was a myth to bust, to use the phrase that the winners are using in the keynote video, that computational geometry algorithms are not implementable. This was a very difficult myth to bust. It took us many years. This is the Seagull project and library. And nowadays, I think you can no longer say this. In recent years, my students drew me back into working on robot algorithms, and I focus on high-dimensional spaces for optimizing the motions of large fleets of robots. I want to pose several topics. One of them, I start from this keynote video where Wissam said, don't give up on model-based planning, which of course I like. And it's a bit against the zeitgeist. And what I want to ask, whether we can have a more refined look at uncertainty, where we check the source of uncertainty, perhaps different aspects of uncertainty can be handled in different ways. The Southop paper looks at different types of uncertainty, but only in the experiments, not in the techniques. The second topic that I want to raise is something very technical. Deep inside the Southop paper, the analysis discusses delta cover for the optimally reachable belief space. I recently discovered the power of delta covers for other problems and for obtaining guarantees on sampling-based methods. I'm really curious about this. It's new to me. Just for those who do not know, it's a very simple concept. It's a collection of balls of the same radius, delta, and a delta cover of a region is a set of boards whose union covers the region. I'm really curious about it. I think it's a very powerful concept if the authors can refer to it in their context, or anybody has anything to add about it, I'd be very curious. The third topic is something educational. We do not often stop to think about papers in hindsight. We move forward all the time, and we have here an outstanding, very influential paper, and I wonder what makes a paper of high research work and paper high quality and potentially influential. It can be useful for anybody to understand it, particularly for young people. So these are my suggested topics, and I'd be glad to hear the other panelists and the winners in particular.
Sounds great. So the person I saw nodding most there and the winners was David. David, do you want to take a stab at that? Picking one of these topics?
I certainly can try, but maybe do you want to ask Wissam to see whether he's now
that's a very good point.
Wissam?
Can you hear me?
Yes, yeah.
Loud and clear.
Oh, excellent, excellent. Okay. So I missed the first part of Dan's questions, but maybe let me try to say what I was trying to say when I was muted previously. I think, but first of all, I want to thank Leslie. I think she's responsible for getting us to do POMDP. So at that time, we were doing some co-teaching and with David as well. And right, so, we were sort of talking and trying to do some work together, and POMDP turned out to be the right topic, right? And Leslie's responsible. Okay, so sort of in terms of sort of getting POMDP practical, like what David mentioned, sort of a lot of techniques. I guess I'd like to sort of put across somewhat of a slightly different angle, that a lot of the problems that we actually want to solve are actually not difficult. And so a lot of problems that I guess AI people want to solve are actually not difficult because humans can do it, right? So it's just because that is worst case intractable doesn't mean we shouldn't try. And we can see a lot of sort of proof of existence, right? Humans can do it, so it really can't be that difficult. So if we start from sort of the easier problem and then sort of try to push the boundary, we'll get a lot done. And I think so that was sort of one of the approaches that we sort of tried, right? We started from the easier problem, we tried to understand what were the easier problems, and then we tried to push it out. And I think I want to connect a little bit to what Dan mentioned, the second question. I think I missed the first question about sort of covering numbers. And so when we initially started, we were trying to sort of figure out what are the easy POMDP problems. And it turned out that if you can cover the space, it's easy, right? Then you can actually approximate in polynomial time in terms of the size of the cover. So, space is small, it's easy. Of course, all the problems most of the problems you want to solve, the space is not small, right? So then we thought about sort of, what we really want to solve is the optimal reachable space, right? The space that the optimal policy gets to, and if we can cover that, then we are done. And that turned out to be sufficient. And then the SASOP sort of a practical implementation or demonstration of that. Okay, I think I'll stop there and let others continue.
Maybe I can just add one more thing since we are on the topic of delta covering number, right? So here's kind of, maybe a generic recipe or generic thought for solving those NP hard and p-space hard class of problems, right? So we all know the hardest instance of the class must be not solvable, intractable. So if we want to solve it at all, we have to, the attention has to be focused on a subset of the class that is actually solvable. So that sort of turns into looking for some kind of a simplicity, right? So delta cover intuitively is just a measure of the volume of the space. small. If the volume of the space is small and we are using sampling methods, then if we turn a single sample into a ball, then a set of balls, a small, relatively small set of balls will cover the space. Once the space is covered, sampling usually would just get the problem, turn a difficult problem into a relatively easy problem, right? So somehow one way or the other, we have to find this simplicity somewhere, right? If it's the space is small, maybe sometimes the output, in this case, the output could be a policy controller is small. Then that's another simplicity property that's very useful that can identify a subclass of solvable problems. And also, but equally important is not only just to identify those properties that make the problem solvable, and hopefully those subclass is also useful and meaningful for robotics, right? Once we take it's like a bit like connecting the dots and taking intersections. When we put them together, if there's a meaningful intersection, then there is a cool paper. Maybe that touches a little bit on Danny's third point as well. And on the first question, Danny raised about we don't give up on the models, right? I think that's a more kind of contentious and interesting and controversial way of stating the issue over here, the model versus data-driven, as if they are kind of diabolically opposite things and therefore they compete and something like that, right? The other day during the workshop, I started to try to think that the robotics problem is just a mapping that takes perceptual input from the sensors to map to an action for robot execution, right? Now, let's keep in mind, a model does not come from nowhere, right? Model comes from there. Model actually comes from data in the first place, right? So model is simply a compact summary and representation of usually lots of data, right? So if we viewed from this angle, what we usually say, call model in robotics is a particular set of models. For example, models for, in the case of PalmDP, that will be a model of system dynamics, a model of observations, a model of reward, right? We have chosen to represent our mapping in this particular way of dynamics, observation, and the rewards, because that seems to, based on our experience, is the best way to decompose this mapping into these semantically meaningful units. And that will allow us to manually construct, handcraft, or learn these models, put them together. And when we have a system that if it goes wrong, we would be able to look at each of these components based on our intuitions and try to fix them, right? So this is our, I would say, let's say that classic robot engineering. Now, what happened in recent years is, of course, that we have lots of data, and then people propose, say, well, okay, so maybe we do not need this decomposition, and say that we just need to treat it as a black box, this is a neural network, and with lots of data, and regress it, and hopefully that we have enough data, and hopefully everything will be automatically fixed. But that happens only if we have lots of data, right? So as soon as the problem or the task becomes more complex, or we don't have as much data, we will go through similar thinkings. Or how do we take this complex mapping to decompose into pieces that will reduce the data requirements for learning, right? In this particular case, for example, we explored, we will take the classic decomposition and turn some of the classic robot algorithm and using the neural network as a programming language to implement those algorithms, and then still regress the neural network using data. And we call that the differentiable algorithm networks. But this is only one choice. This is a particular choice of a particular structure I impose on the network. Maybe there are other alternative choices, right? In particular, because of the choices we imposed, maybe that it reduces the dimensionality of the space in which we need to explore. But because of those constraints, that the shape of the space becomes more complicated. Their optimization becomes more difficult, right? So maybe in order to learn those models more effectively, we may need to explore alternative decompositions that's easier to learn, but nevertheless would exploit the structure to improve the performance of learning. Yeah, that's fine.
So if I may add a little bit, so even for POMDP, we don't actually forget the geometric model actually. So it's actually embedded in the transition and also in the reward function we have. And some of the speed up we have from the sampling strategy, some of them actually utilizes the information of the geometry from the environment or the state space that actually speed up the sampling as well. So yeah.
So that's polite of Danny to nod, because that's my mistake and I stand corrected. So thank you. But Ron, do you want to jump in? Do you have any thoughts on any of Danny's questions?
Yes. So Danny raised, I think, a really good question at the end, which especially for a lot of the PhD students and junior people on the call is really important, which is what makes a paper influential, especially in the way that Sarsop was. And that's a really good, important question to always think about whenever sort of publishing a paper is how do we maximize the influence of this paper and so forth. So I think that the three sort of big features, I think, of a really strong paper, there are three features, and I think the Sarsop paper really had all three. And the first one is that it's an important problem. And I think POMDPs and solving them efficiently is a very big, important problem because of the broad applications in so many different areas of robotics. And we saw that in the plenary talk, sort of the list of different sort of domains in which the Sarsop code was used, from collision avoidance of aircraft to human-robot interaction challenges. Just really the broad applicability of POMDPs makes it important, and hence solving them efficiently was important. And that was part of the big sort of contribution here with Sarsop. The next big feature that I think, to follow up with Danny's point about what makes the paper influential, is a really strong result. So it really makes a big step forward compared to the prior state of the art. And in particular, allows us to be able to solve problems that we couldn't solve before. And Sarsop paper did that too, in the sense that by decreasing the compute time so dramatically for these POMDP-based problems, that made a lot of problems that were practically impossible before now practically solvable. Essentially, going back to what Leslie said, the view of intractability was diminished because of that speed up. So that was sort of the really strong result. And I think the third part of it is getting the visibility. So a really strong result can sort of be published in something that nobody sees, and then it doesn't have the influence that it possibly should have. And this is, I guess, a good idea to submit it to RSS, so you get the visibility from the community here, which sees the work and uses it and builds it. So visibility was achieved there by publishing in a strong venue with good, strong peer reviews. So I think the intersection here is really across these three areas of having an important problem and strong results and visibility. And all those are good features of achieving an influential paper. And Sarsop did achieve all those.
Thanks, Ron. That's great. Actually, you were a bit out of. I had you jump in because I thought you would have some valuable things to say there, and of course you did. But let me just give a little bit of a rationale for why I thought that Ron would be an excellent person to have on the panel. Partly because you work on planning under uncertainty, but you also work on extremely, extremely valuable problems which would be. We would all prefer to have, better needle steering, for example, right? It would make a huge significant impact on the lives of many people. And that's also an insanely hard problem. So complicated. It's sort of hard to imagine where to even get started on that. And so I thought I would ask you a little bit about your sort of point of view on what the future of that problem is, and whether whether it is to treat the problem as a POMDP, should we say POMDP from end to end, or whether there's some other aspects as well there. And so it might be useful for you to kind of talk a little bit about that work, and then perhaps Hannah and David Wee-Sun can kind of respond to your thoughts.
Yeah, well, first off, thank you, Dylan, again for organizing the session, and of course, congratulations to Hannah, David, and Wee-Sun on the paper. So following up on Dylan's question, I can give some background about medical robots, especially on how POMDPs sort of fit into that. So I think a really important problem that robotics can help address is improving patient care. And a step in that direction is, can we take medical procedures that are currently performed by hand and improve their precision and accuracy by creating medical robots that can help accomplish them? And in particular, can we automate those medical robots to really take advantage of their full potential and again, increase the accuracy and precision of the procedures and consequently enable better patient care? So a big building block of enabling a robot to automatically perform a procedure is motion planning. So we need to sense what's going on in the tissues. We need to plan what should the robot motion be to accomplish that task, and then we need to actuate that. But of course, automating a medical procedure is hard, and a big reason that that is hard is that the motion planning really has to consider an immense amount of uncertainty. So if we look at medical applications, and I think this is a great exemplar of sort of like the challenges of uncertainty in general, just sort of as a particular application area that just has a massive amount of uncertainty, and hence formulations like POMDPs become very relevant, is that first of all, we have a lot of motion uncertainty. So as medical devices become smaller, more compact, and more minimally invasive, so they cause less sort of collateral damage when doing a procedure, the combination of that trend, or the consequence of that trend, is
Oops.
I don't hear Ron.
would like this to be as thin and non-invasive as possible. So current commercially used medical robots are oftentimes more manipulator-based and bigger, and making them smaller sort of increases that uncertainty, so your forward kinematics models aren't usually as accurate. So motion uncertainty is one big part. I think another big part is the partial observability. Sensors are getting better in many domains, but when dealing with medical applications, there's a lot of inherent challenges. So what is the state of the device? With something like an industrial robot arm, forward kinematics can be very accurate. That's not going to be the case for a medical device that's often highly flexible, and so the kinematic model will be highly uncertain. So we can use things like electromagnetic trackers to try to track where are you in 3D space, but those also have some uncertainty in their measurements as well. There's also the question of what's the state of the environment. So there's a big representation question there, but environments inside the body are even harder to model, or substantially harder to model than, for example, the rigid world you would have in a factory, or even a semi-rigid environment if you're dealing with something like self-driving cars, where sort of objects are moving but can be approximated as rigid. Inside the body of highly deformable tissue, it deforms in weird ways. You have your robot potentially deforming as it interacts with deformable tissue. So there's a lot of uncertainty there, both in the robot's interaction with the environment and the environment itself. And we have sensors like X-ray images or CT scans, but as is always the case in medical applications, you get a sensor that gives you lots of data, but then it causes harm to the patient. You can't take too many X-rays or CT scans because then the radiation dose becomes harmful to the patient. You can use something like MRI, which you can use at greater frequency, but then because of the physics limitations of how MRI works, you're going to get essentially low resolution or low frame rate, depending on the trade-off you want there. So that sort of highlights, I think, for medical applications as a big frontier of sort of pushing the boundary of motion planning under uncertainty and POMDP problems, but it also sort of highlights sort of the broadness of applicability of POMDPs, because essentially you have the partial observability due to the limitations in sensing. You have the Markovian property here, in the sense that there's all of this uncertainty in your motion, where a lot of it can be modeled as sort of erasing some of the prior history. And furthermore, it's a decision process, because in order to automate a medical procedure, you have to make these decisions of what's the action that you're going to perform. So I guess as we move toward using sort of more general POMDP solvers in domains like medical robots, there are just a lot of challenges to solve. If I look sort of historically at the trend, people have sort of looked at these really hard problems, especially in the medical domain, and developed a lot of customized solvers. But one of the big benefits is, of using a more general tool like SARSOP and invariance is, can we have a more general tool so we don't have to look at an individual robot, an individual procedure, and develop a customized algorithm? Can we sort of look at these really challenging scenarios and have more general tools that really solve them in practice? And that, I think, is sort of like one of the next frontiers, even harder, larger scale problems with continuous action spaces in cases where we don't have well-defined models, or we need to learn models, and developing tools there. So on these really challenging problems, I'm, I guess, just really interested in people's thoughts and sort of next steps on work on POMDP solvers that we can use to sort of address this sort of like next generation of really hard problems.
Thanks, Ron. That's an excellent question. I mean, I guess to me, it begs the question of, is expected reward an appropriate thing to maximize in those cases? And maybe that's just because I'm only aware of the sort of classical results, but maybe we should start with you, because you always get the short end of the stick. You're coming in and you're nodding. So if that's okay, do you want to take it away on that?
Okay, yeah, I think your question about whether expected reward is the right thing, possibly it's not, right? And I think maybe Ron would have a better idea of whether it is having worked in the domain. The expected rewards are what we have been working with in POMDP. So it's possible that it's not, and if it is not, then I think the question comes up like, what would be the right type of reward, or what would be the right formulation? Maybe not the reward formulation, but maybe some other formulation. And if we have some other formulation, then what's the right way to go about solving it? So I don't have the answers to that, but I think that raises interesting questions that maybe potential grad students can think about. Right, okay, yeah, and back to the domain of medical applications, it's really important. I think one drawback, okay, so from the robotics side, is probably not so bad. I think we can build models of robots. We can get enough data, right? So from the environment side, maybe that's much harder. If you don't have a lot of data, then it might be difficult to build the models. So I think there's interesting challenges there, right? When you have limited data on the medical side, how do you build the models? And it's sort of interesting because I think you can build good models of the robots, right? You have them, you can play with them, you can get lots of data from the robot. So it's sort of a problem where you have sort of a bit of a mix. On one side, you can get good models, on the other side, not quite. How to approach it again? No, right now I don't have good ideas, but interesting problems to work on. Okay, I don't think I have more to add at this point.
I can jump in on Dylan's question as well, because it relates a little bit to Wee-san about this rewards, because I think it highlights this question of difficulty of modeling. So Dylan, if I sort of understood your point here is, are we still, historically we've looked at maximizing rewards, and are other applications, for example, where we want to look at different types of objectives in essence. I would argue that the rewards formulation in the POMDP is very general, and I think really applies like even in the medical domain in an effective way. So what's the reward? If you're looking at something like a healthcare application, what's the reward? Maximizing lifespan of the person being treated from this particular ailment that they have. That's ultimately the reward. So improvement in patient care, meaning that the patient survives and lives on. That's reward. Now, mapping that to how do we formulate a reward for specific actions, that is going to be the hard part. And that's essentially where, this is now speculation. That's a research question. How do we do that? How do we do that? And possible ways of doing that is that it seems like data is a possible way of trying to learn those mappings potentially. I think in domains like healthcare, there's sort of a delayed effect of getting a lot of data. If you're solving a problem in machine learning about identifying cats, you've had huge data sets for quite a few years now by doing image searches for cats, and now you can learn to identify cats in images. In healthcare, data is much more restricted, but in some sense, the data is out there. The hospitals know patients underwent this treatment. During the treatment, these images were taken. What does that mean then for the outcome of that patient in terms of lifespan and recurrence of returning to the hospital? There's increasing amounts of that data being recorded in electronic health medical records and things of that sort. Can we start to leverage these forms of data, try to figure out how to map those real rewards that we care about to actions? And that's a very challenging and interesting question in terms of learning and creating those mappings. Because once we do that, then we can really leverage a lot of these more traditional approaches I'm certainly called star sub-traditional, I guess, because it's been around for over 10 years, but mapping to these, to formulations of POMDPs so that we can start to maximize rewards.
So can I jump in a little bit? So I think medical might not be so bad for POMDP in the sense that I think if you want accuracy, usually we do need the quantification. I mean, one of the things of POMDP is that you quantify uncertainty carefully, right? So it seems to me if your goal is wanting to get accuracy, that's one way of handling uncertainty, that you actually quantify uncertainty carefully, and so in that conceptual sort of high level conceptual thing, it seems to match. Right? In terms of data, what I'm not too sure is that yes, even if you have lots of CAT scan data or MRI data, to my understanding, when you want to do surgery, it's usually on not exactly a perfect functioning organ, right? So I don't know whether it has deformed from the the many data that you have, because usually I suppose the many data you have might be sort of healthy people, or even if they are sick, maybe different types of sickness, and that might have different relevance, right? Which then brings up the reason why POMDP becomes important again, because at least from some of the results we have, POMDP, embedding POMDP inside the machine learning, for instance, can reduce the data requirement. So then perhaps even if you just have a small number of data of people having a particular disease, that could still be useful, for instance, and that can help generate the model after that. So I think that's why I think medical might not be so bad for POMDP. Yeah, in terms of the objective function, there are actually many different types of objective function as well in POMDP. It's just the one that we work on are basically on maximum expected reward.
If I may add a little bit here, right? I love to talk to people like Ron, and we learn a lot from people like Ron. In fact, we were talking 2 days ago, right, Ron? And I think it's about to understand the sources of these uncertainties and identify the key characteristics that will enable us to solve it, right? So I think when I was listening to Ron, basically I'm sort of taking it apart into the modeling part and the algorithmic part. Now, the modeling part, I think the issue here is indeed the reward function. I think I probably share Wissant's view that I would be worried a little bit about the mean average reward. And Ron, remember the other day we talked about, you were mentioning about certifiability, right? Yes. I think that the average does not provide a whole lot of certifiability, right? So I would feel more comfortable if we can have a high probability guarantee rather than just an average, right? So, but fortunately, I believe my intuition is that for example, our despot algorithm, which is the online version of the POMDP solver, and that algorithm, even though POMDP is the classic formulation of POMDP targets for average reward, our algorithm, in fact, I believe, I didn't track the math, but my intuition is that it can solve for a high probability guarantee as well. That is likely to be true. Now, the other part is about the algorithms. Well, I think the solution to a POMDP or a solution to an decision-making under uncertainty is basically looking for approximations, looking for principled general approximation. This is the way I will say it. Now, and also characteristics that tells me that, oh, this is something that I cannot cut corner of. There's one thing Ron said, I realized, oh, this is the sort of the primary trait of POMDP, which is that, oh, if you make an observation that has a cost, that is one trait of a POMDP. If you hear this must be a real POMDP. You cannot turn that into some kind of Bayesian filtering because it involves the essential trade-off of gathering information and paying a cost for that. That's the long-term reasoning of POMDP that would actually do it for you. And probably no other tools I'm aware of can kind of do this in a principled way for you.
So that's great. That's sort of a reminder of there's the separation principle guys, and there's the POMDP guys, and
Right.
and there are problems for which, yeah, that separation principle is just a horrible approximation. So I'm keeping an eye on the time here because that's my job, and I'm going to ask a different question, a different temporal question. So this paper has won the Test of Time Award because looking back over the past, it's been influential, and it's a very well-deserved award for that. But now I want to turn the tables a little bit and try to look towards the future. And so, you know, one of the traits we tend to use is we use the past to predict the future. And so one of my initial thoughts here is that if this has been the increasing coming of age of POMDPs, and they're more and more practical than they've ever been. The question is the future going to be seen through the POMDP lens? Are we going to treat robot problems in the way that David has posed in his part of the presentation, where he said, think about it as a function mapping, and then are we going to use the structure of POMDPs and models, or are we going to be a bit closer to the later portion of the talk where Wee-Sun was saying, well, we use some of the structure, but then we differentiate through that and use that. So that's my question. And I thought maybe Leslie, you've been quiet for a while, so maybe I'll ask you to start with that one. But I think it'll be a good one maybe for Danny to speculate on as well. Given that we're all wearing our speculation caps, right? So we know that predicting the future is hard. So
yeah. Well, no. So I mean, this is the question that we're all just struggling with right at the moment, and I think everyone understands that in principle, a totally generic wad of recurrent neural network goo could learn to do any POMDP policy that we could derive in some other way. So there's no, in principle, argument that you have to do it this way, I think. But on the other hand, human engineers like us have to actually somehow help make these systems. And I think that the insight that we have about algorithmic structure, about formulating some kinds of spaces, gives us really good bias and priors and so on. And so I think the reason, going back to the thing I said at the beginning, these problems are fundamentally, the problems are POMDPs. And the question is not, is it a POMDP or not? The question is, what solution strategy are you going to take? And, I think in some cases, it's actually may be easier to straight up learn the policy. Putting a key in a lock is a POMDP problem, but it is just easier probably to learn the policy than to try to make the model. But there are other problems where it's easier to make the model. And we just, I think, have to be as intellectually flexible as we can about looking at problems and trying to intermingle all the insights and techniques that we have.
Cool. So how about you, Danny? Are you intellectually flexible? Have you been doing some
I
yoga
love
there?
the term. I love the term. I think that's something that many of us lack. I think the key is intellectual flexibility. I love it. I don't know what will happen in 5-10 years from now. Everything is changing very, very fast. I hope there will still be some place for reasoning about first principle, but perhaps when we meet in 10 years from now, there will be one big black box, and we'll throw everything into it, and it will solve all our problems. I tend to suspect that it will not happen so soon, and we will need to understand problems in depth, and I don't expect to have a magic bullet that will solve all problems. Not in the very near future.
Yeah, if you're betting against magic bullets, that's probably a pretty safe bet. I'll give you my money on that one. Yeah. So Wee-Sun, what is your thought on this? I mean, this seems kind of most closely related to the portion of the talk that you presented in your work there, and maybe you can kind of make this concrete in the sense you could maybe talk a little bit about what happens where if you start with a POMDP and you've actually got a policy that where you've used a quote traditional method to solve it, and you start with that, and then you run gradient, stochastic gradient descent on that, and you discover that, oh, the policy changes in a way. Maybe that means that this is compensating for some errors in various places, or is there something from your experience maybe you can reflect on there?
Okay, yeah, I guess, if we had a POMDP, it's interpretable, it's nice, but often we don't have the right model of the world. So, so what we talk about at the end of the talk is that, right, we can compensate for that by sort of doing sort of end-to-end sort of learning, and it can compensate for that, but then you lose some interpretability, right? It fixes the error that you didn't know about in the first place, so then you probably don't quite know what's happening there. So there's a tension there. I think, right, to resolve that, if you really need the interpretability, then you're going to have to work very hard to build really good models. To build things in the real world that works, then perhaps you might be happy with sort of a bit of a trade-off, and then because of the limited amount of data that you have, then, right, you might be happy to engineer something that works well, sort of having a bit of a trade-off. So David and I had an interesting conversation yesterday, I think, right? So we were trying to figure out sort of, right, what's the possibly right way to go in the future, right? We could build simulators and then, run this big coup that Leslie mentioned, right? And then, we could solve problems that way. But we realized that we are sort of, if you do that, you're not really reducing the amount of work, because it's a huge amount of work to build a simulator. You have to get all this data, right? So if we go back to what David was saying at the start of the talk, right, that if you look at the whole system as a whole, right, you have to get data from the real world to build the model. You can't cheat, right? You can't say I have the sort of simulator in the first place and therefore data is free. So you have to look at the whole world together, right, to build the system. And if you do that, then I think most likely you want to figure out the trade-off, right? Do you want to think hard, get the structure, and then therefore be able to reduce the amount of data that you need to get from the real world? Right, what's the right trade-off? There's sort of no free lunch here. Right? If you want to say that, I can do learning, but then you need data, so you need a model, and then you need to get the data. Right, by looking at the whole picture, you can sort of hopefully figure out where do you want to do the trade-off? How much thinking do you want to do to build the models? And then how much data do you need to get from the real world? If you think harder, maybe you need to get less data. If data is very cheap, then maybe you don't need to think so hard, and then you can throw the goo and your supercomputer at it.
So you've said it in a way which is very carefully treaded the line of not being pejorative and saying that people who are learning are not people who just don't want to think, but very, very close to that line, but on the right side of that. Yeah, that's great. So I wanted to ask another question, because one of the things which kind of amazed me was that, I'd read papers on POMDPs and seen tiger domains and such things. And then when I saw a golf cart driving amongst the crowd, I was like, wow, this is not solved on paper. These guys have really, really cracked this nut. And so I wanted to ask a little bit about the systems aspect. Hannah, for example, showed in her portion of the keynote several grasping experiments and so on. And so I wanted to kind of, that is a substantial amount of work to do all of to do the systems component. And this is, after all, robotics science and systems. Could you guys reflect a little on sort of what it took to do that? And maybe Ron, do you want to jump in?
Well, why don't I just give the people, Source-Up authors, a chance to talk about that.
Fair enough. Okay.
So for the manipulation experiment we do, so basically, obviously it comes when we need to develop the model first. That's usually when we start with the POMDP, right? So, but the thing with generating POMDP model, we realize, well, at least for the kind of application we look into, right? We are not looking into like medical, so it might have a pretty high risk. But for the kind of application we do, in many cases, I know the model is not perfect. So I'm pretty sure the uncertainty model we have in those applications are not perfect, are not actually faithful. Because what we did was we gather data, but it's a small amount of the data, and we basically do fitting to figure out what's the right probability. But that turns out to work pretty okay for the kind of task we want, and including some of the tasks in like trying to open a little bit harder valve and things like that. But we do need to sort of figure out the right amount of. So we need to design what's the set of actions we want to have, for instance, and also the kind of reward functions we want to have. That's usually one of the keys as well in generating that. Right? And then obviously once we have that, we combine it with the perception side. Now again, with the perception side, for us at least, for my side, we didn't work so much on the perception side, and so as you can see that in that video, it's not exactly great perception. But one of the things we want to show is that even when we don't have good perception, when we have quite noisy observation, we can still handle those kind of things as well. So that's some of the things that we did in those demos. So the other thing that I think is nice though, once you generate that POMDP model, then when we try to move to a slightly different problem, as in a slightly different robot, for instance, then it's not that difficult to actually do the transfer. So obviously we don't need to do much retraining, for instance, if I take the machine learning one, right? So in some of the cases, we can even just plug it in to the new model, but obviously we have this component that has the collision check that use computational geometry that needs to be replaced, right? But that's just replacing the 3D model we have, and that's it basically. So that's some of the nice things about using POMDP in the realistic world as well.
Maybe I'll just say one little thing about POMDP, and I think, getting it to work on sort of realistic problem. Just to echo Ron just now, the reward function's hard. Right? What's the right reward function to do the things you want it to do? I think that's one of the hard things. It's mathematically nice, but then to get it in the real world, we don't actually know the right reward function often. So, yeah.
Well, we're at the top of the hour here, and so I know there are a few people who've got other things other places they need to be, and so forth. So I just wanted to say thank you to everyone who made the time in your various time. I mean, this is really early in the morning if you're in Singapore, and so thank you or Australia, I guess, right? Thank you for doing that for us, and also to each of our panelists for thinking about the topic, engaging with the panel, and providing sort of lots of food for thought. So thank you, everyone.
Thank you, Dylan, for organizing.
Thanks.
Thank you.
Thank you.
That's absolutely my pleasure. It was another one of these cases when I saw the award, I thought that makes sense. That's the paper that I would have expected had the cumulative impact. And I do think that it's important that I think we kind of do try to think about papers. I'm actually skeptical of the word impact, because it's a force over a very short period of time, as opposed to what we really want to think about as an integral of something. right? And so this Mark's innovation of introducing this award, I think really, if it can modify a little bit of the sorts of papers that people tend to write, or how we think about how we value papers, perhaps we think less about sort of immediate fanfare and a little more about the long-term staying power of the community, that would be great. So with that, I am next going to move on to the awards that we have for RSS 2021. And I'm going to do that by sharing my screen here. Attempting to share my screen here. And all right, hang on, give me a second here. Okay, so that concludes our panel. And so next, I'm going to talk about the awards that we have for the papers this year. And this was our awards committee. Thank you, kudos to our awards committee who made the time to virtually visit all the posters, and they were able to look at the papers and of course look at the spotlight videos and so on. And as a reminder, we had these 6 papers as our award nominees. Now, traditionally, we've split them into award nominees for student papers and for general papers and for systems paper. And several of these papers straddled that divide. And I was nervous about some of the papers being excluded because they were being considered only in one category or in another. And so we treated this sort of as a flat list. Now, before we go to the paper award nominees, the paper awards, there's an award which the committee didn't put together, but which came from feedback solicited from authors. And there were a few people who wrote to me to say, thank you very much for the reviews that we got. And of course, the reviewers are the unseen heroes, right? The conference can't be a success without people who spend the time, who really read the papers, who try to give constructive and insightful input. And so I'm going to try to see if we can use this multimedia here. And the winner of the Outstanding Reviewer Award for RSS 2022 is Lawson Wong. Congratulations, Lawson. Thank you. I know mostly people assume that this is anonymous, unrecognized service, a thankless task, but I'm thanking you, and I think we're all thanking you. So thank you very much for that. Okay, so on to Best Student Paper Award. Oh gee, I don't have a drum roll here, but okay, so there it turns out that my previous suspicions about the 6 cases was reasonable, because the awards committee wrangled and discussed and argued, and in the end they came back to me and said, do we have to choose one because there's a tie here? And so this year we're giving 2 Best Student Paper Awards. And so cue the drum roll. Okay, and the first Best Student Paper goes to the paper Learning Riemannian Manifolds for Geodesic Motion Skills by Heidi Baker Mohammadi, Soren Harburg, Georgios Avenditis, Gerhard Neumann, and Leonard Rozzo. Congratulations. And the second student best paper goes to the paper Dissect a Differential Simulation Engine for Autonomous Robotic Cutting by Eric Hayden, Miles Macklin, Yash Narang, Dieter Fox, Animesh Garg, and Fabio Ramos. Congratulations, guys. It's a small pool to get your paper into RSS, and to be recognized as a nominee is I think a big deal, and so and to win is excellent. So congratulations, applauding, and so forth. Okay, so we have one more award, which is the best paper for RSS 2022, except the committee came back to me and said, there has traditionally been a best paper award and also a best systems paper award. And this best systems paper award is in memory of Seth Teller. And it's it's not an award which is necessarily given every year. The proviso is that there has to be seen to have been some exceptional systems work. And in this case, the committee has recognized a paper which is wins both the best paper award and the best systems paper award. And the winner of that paper is TARE, a hierarchical framework for efficiently exploring complex 3D environments by Chao Kao, Hongba Zhu, Howie Choset, and Ji Zhang. And I have to say, when I looked at handled all the spotlight talks, this was a unique spotlight talk in the sense that the very last sentence said, if you come by the interactive session and pop by a poster, you'll see a live robot demo. And I thought, first of all, do they know that we're not actually having an in-person poster session? And second of all, how would you know if it's a live poster demo, a live robot demo? And then someone said, well, you have to have the robot carry today's newspaper or something. But indeed, if you popped over to that poster, you'll see that they did show a video of real robots running about and running their framework. So congratulations, very, very well deserved. PDFs of certificates, both to the nominees and to the award winners, will be dispatched post haste. So look in your inbox for that. Again, congratulations, everyone. Okay, so now we actually have a 5-minute breather, and then we're going to reconvene in Gathertown, and we have our final interactive poster session, which will run for the same 75 minutes as all the other poster sessions, and then we'll come back and we have our final session where you can hear about plans for RSS 2022. So I hope to see you all then, and thank you very much.